My name is Markus and I'm presenting Treewidth-Aware Quantifier Elimination and Expansion for Quantified CP. This is joint work with Johannes Fichte and Maximilian Kieler.
So what is this Treewidth all about? Well, in general, there are lots of problems that are rather hard on arbitrary graphs, but these problems typically become rather simple if we look at the special case of a tree.
Well, and the treewidth now is a way to measure the closeness of a given graph to being a tree or the tree-likeness of a graph.
While treewidth was originally defined for graphs by Robertson and Seymour in a series of papers, nowadays having bounded treewidth k can be seen as one of the most cited combinatorial invariants. In fact, assuming instances of treewidth k renders a large variety of NP-complete problems tractable. We call this tractability fixed parameter tractability since it depends on fixing the parameter treewidth k. In such fixed parameter tractable or FPT algorithms for treewidth, the complexity or the hardness of a given problem is confined to this parameter treewidth. This allows for a more fine-grained analysis where we get polynomial runtime, but in addition the runtime also depends on the value of a function depending only on the parameter treewidth k. In classical algorithm analysis, where we do not have this fine-grained tool, we often only consider instance size and cannot confine the hardness of a given instance to some parts.
There are also plenty of FPT results for problems believed beyond NP, like deciding the existence of a solution to a quantified constraint satisfaction problem. Chen showed that this can be done in a runtime that is L-fold exponential in the treewidth, where L is the quantifier rank of the QCSP formula. More precisely, the runtime is a tower of 2's of height L-1 with the size of the domain to the power treewidth on top.
One possibility to obtain such results is by using the well-known theorem by Cosell. While this theorem can be seen or can be used as a rather powerful classification tool, it might not serve well in defining the exact runtime depending on k.
This brings me to our contributions. We showed that under reasonable assumptions like the exponential time hypothesis, one cannot significantly improve the result by Chen. So under ETH there is not much hope to obtain a runtime for a QZ that is better than L-fold exponential in the treewidth with the domain size to the treewidth on top. Interestingly, this result relies on a novel reduction for Treewidth-Aware Quantifier Elimination, which only single exponentially increases treewidth. The overall reduction is Treewidth-aware and is actually guided by a tree decomposition and simulate parts of dynamic programming along the tree decomposition. We also provide the reverse direction where we establish a reduction for exponentially decreasing treewidth at the cost of an increase of quantifier rank. Assuming ETH, one cannot expect to significantly improve the treewidth increase or decrease of our reductions respectively.
This now brings me to the core idea of our reduction. Most lower bound reductions for treewidth we have seen so far start from a given SAT instance of treewidth k and construct an instance of the desired problem where the treewidth is a function in the instance size or the number of variables of the SAT formula. So in this case, to show a lower bound for QZ2, we construct an instance of QZ2 where the treewidth is logarithmic in the number of variables of the SAT formula.
Our approach, consisting of a reduction for increasing quantifier rank and decreasing quantifier rank, is completely different in this regard. So our reduction for decreasing treewidth starts with a CSP instance of treewidth k and constructs a QCSP2 instance whose treewidth is logarithmic in the treewidth of the CP instance where we started from. Our reduction for quantifier elimination reverts this. So it starts with a QCSP2 instance of treewidth k and construct a CSP instance whose treewidth is exponentially increased. For the former approach, however, it is not easy to see how to generalize it. The reason for that is that the treewidth of the resulting instance does not directly correspond or relate to the treewidth of the instance where the reduction started from. So reducing from SAT to QCSP3 essentially requires a different idea. Our reductions, on the other hand, can be easily extended and applied to further cases. So we can, for example, reduce from QCSP-L to QCSP-L plus 1, thereby exponentially reducing treewidth. However, we can also apply the reductions several times, thereby reducing, for example, QCSP-L to QCSP-L plus 5. Similar arguments also hold for our reduction that applies quantifier elimination.
So what has been done so far?
In the early 2000s, the ETH was proposed.
The exponential time hypothesis, or ETH for short, implies that we cannot solve satisfiability of a given formula in better than single exponential time in the number of variables in the worst case. And while this ETH is widely believed, it's actually stronger than P is not equal to NP. So it might be the case that ETH fails, but still P is not equal to NP.
So we have that Treewidth alone is not sufficient to obtain an FPT result for QCSAT. Then there was also rather recent results showing for Boolean QCSAT that it cannot be solved in time better than double exponential in the Treewidth. Then, a year later, it was proposed to use Boolean QCSAT as an alternative to Cosel's theorem. This is mainly motivated by the precise upper bound that one can get using chance results. Rather recently, we showed that one can probably not significantly improve chance results under ETH for Boolean QCSAT.
A similar result was mentioned for odd quantifier ranks by Pan and Wadi in an earlier work.
Before we go into details, we briefly provide some background on quantified constraint satisfaction problems and QCSAT. An instance of QCSAT consists of a quantifier prefix and a matrix. The matrix is a CSP over some domain D, where each constraint is a set of allowed assignments of some variables to D. As already said, the quantifiers are alternating, and what we assume here is that the last quantifier is actually existential.
Here we assume that f is closed, meaning that every variable of the formula occurs under exactly one quantifier.
And we are interested in the problem QCSAT-L, which asks for a given QCSAT-Q, whether Q is satisfiable or valid. Satisfiability of a given QCSP can be easily defined via recursion.
So for all x q is satisfiable if for any assignment involving the variables x, q under this assignment is satisfiable, and further, exists x, q is satisfiable if there is at least one assignment involving the variable x such that q under the assignment is satisfiable.
Consider now the following example, where for brevity we actually denote constraints as formulas. So we have the QCSP formula for all Wx exists yz over 3 constraints and domain from 0 to 4. Intuitively, this formula is satisfiable because no matter how you set w and x, you can always set y and z to some value, namely z to the value that w has. Y gets assigned w plus x, but if w plus x is smaller than 1, y gets assigned 1, and if w plus x is larger than 4, y gets assigned 4. With this strategy for assigning y and z, it is easy to see that the given QCSP is satisfiable. So let's now come back to this tree width, or this measure of tree likeness of a graph. Well, in fact, tree width can be defined in terms of tree decompositions.
A tree decomposition of a given graph is an arrangement of the graph into a tree, where each node of the tree, referred to as bag, gets assigned certain vertices of the graph. This has to be done in such a way that the following three properties are satisfied. First of all, every vertex has to occur in at least one bag. In our example here, we see that this is the case for all the vertices of G. Then all the edges have to occur in some bag, meaning that for an edge, the two vertices of the edge have to occur together in at least one bag. Here we see that this is the case for the edge AX, BX, and AB, but we can check that this is true for all the edges of G. Last but not least, we require the connectedness, which basically ensures that if we restrict the tree to a certain vertex of the graph, the result is still connected. In our example, we see that this is the case for C, also for B, and for X, and finally also for vertex A and Y, since both vertices occur only in one bag. So this is indeed a tree decomposition of our given graph G. The width of a tree decomposition corresponds to the largest bag size minus 1, which is 2 in our case, and then finally, the tree width of a given graph G is the smallest width among all potential tree decompositions of G. The last missing ingredient we need before talking about details of our reduction is so-called dynamic programming on tree decompositions. So how does this work? Well, first we assume a given propositional formula. Then we compute the tree decomposition, but for that we need a graph representation of the formula. Here we use the so-called primal graph, where as vertices we have the variables of the formula, And we have an edge between two vertices whenever the two variables occur together in at least one clause. Similarly, this can be done for constraint satisfaction problems, where we have as vertices the variables of the problem, and we have an edge between two variables whenever the two variables appear together in at least one constraint. So assume the given tree decomposition, which you already know, of the primal graph of the given formula. Then dynamic programming on the tree decomposition performs a bottom-up or post-order traversal of the tree and computes for each tree decomposition node a table. Whenever we introduce a new variable that has not been seen in the current subtree during the traversal, we need to guess a truth value for the variable. In the leaf node containing bxa, we need to guess 2 to the 3, so 8 many truth assignments, and then we check the corresponding clauses of the bag, meaning not A or B or X and A or B. This leaves us with 5 rows. This is then continued for the next node, where we take the previous table, project it to B and X, introduce C, and check all the clauses that only use bag variables, which leaves us with the next table. We continue like that and compute the tables until we reach the root node, where we have to merge agreeing assignments. Since the root table is not empty, there has to exist a satisfying assignment, which can be easily reconstructed by following back predecessors of rows. With this technique, we obtain an upper bound for Boolean satisfiability, which runs in time that is single exponential in the tree width. This technique can be easily extended to CSP instances, and it can be even used to solve QCSAT. Okay, wait, but what does this upper bound technique have to do with our reduction and obtaining the lower bound? Well, our reduction is highly influenced by this technique. This now brings me to our reduction for exponentially decreasing tree width at the cost of an increased quantifier rank. Next, we are ready to outline our reduction. Maybe as a disclaimer, this is not, so to say, 100% our reduction. This is, as already mentioned, the outline, and I only want to give main ideas and important ingredients of our reduction. This outline highlights the following. On the left-hand side, we see a tree decomposition of the primal graph of the matrix of a given QSAT L instance. And on the right-hand side, we see a corresponding tree decomposition of the primal graph of the matrix of the resulting QSAT L plus 1 instance. So we basically see a one-to-one correspondence between a bag of a tree decomposition of the input and a bag of a tree decomposition of the output. And intuitively, in a bag on the right-hand side, we want to do the same thing, more or less, as in a bag on the left-hand side. It's just that on the right-hand side, we're not allowed to have as many bag elements as we have in a corresponding bag on the left-hand side. So how do we go from bag size k in the left-hand side to bag size log k in the right-hand side? Well, in each bag on the right-hand side, we are only allowed to address, say, a constant number of vertices in the bag on the left-hand side. Technically, this is realized with the concept of pointers similar to programming languages, where with a pointer in a bag on the right-hand side, we can address at once any element of the corresponding bag on the left-hand side, but only one element at a time. Here, pointers are represented via these green P elements. The overall reduction consists of 3 parts called guess, propagate, and check. In the guess part, we guess similarly to dynamic programming algorithms the value for introduced variable. However, for each introduce of a variable, we need fresh copy variables given in blue to do that. In the end, it is ensured by the propagate part that these copy variables have the same value by synchronizing pointers using the red squiggly arrows. Let's now have a look at our example as already quickly discussed. In the figure we see first the primal graph and then a tree decomposition of the primal graph. Our reduction R up takes Q and the tree decomposition T and constructs a QCSP3 instance that is satisfiable if and only if Q is unsatisfiable. The quantifier structure of the resulting QCSP instance is as follows. Intuitively, the quantifier structure is inverted and we have to take care of additional copy variables. Since the universally quantified
quantified variable w is introduced in node T1 and T2, we have WT1 and WT2 existentially quantified. Similarly for xt1, for the former existentially quantified variable y,
we are only allowed to keep one copy variable under universal quantification, and we have to shift the other copies to the next existential quantifier. Intuitively, in the end, we want to have that the values of these copy variables are identical. So the shifted variables have a clear existential dependency on the one copy variable that is universally quantified. Additionally, we add universally quantified pointer used for representing a pointer for each tree decomposition node, and we also need existentially quantified pointer values, which give the value of the corresponding pointer target. So how do the formulas for the guess part look like?
Whenever we point in T1 to the first variable, namely w, then WT1 has to coincide with the value of the pointer in T1. Similarly for the second variable x and the third variable y of node T1. The cases for node T2 are analogous, and since T3 does not introduce variables, this completes the guess part.
As already quickly mentioned in the outline, the propagate part is responsible for synchronizing pointers.
Whenever we point in node T3 and in node T1 to w, then the values of these two pointers have to coincide. Analogously, if both pointers target y. Similarly, also pointer values of nodes T3 and T2 need to be synchronized.
The check part is a bit more involved.
Additionally, we require constantly many pointers and pointer values for each tree decomposition node. Here we assume that the arity of each constraint of Q is constant. These pointers also require synchronization between two neighboring tree decomposition nodes. These pointers allow to check for unsatisfiability of constraints, and this information of unsatisfiability is passed and guided along the tree decomposition. At the root node, unsatisfiability is enforced.
For this check part, we require additional existentially quantified pointer as well as pointer values and variables to guide the satisfiability information.
Having established the reduction for exponentially decreasing tree width, this now brings us to our reduction R down for quantifier elimination at the cost of an exponentially increasing tree width. The core idea of the reduction R down encodes parts of dynamic programming along the given tree decomposition. This part of the instance is restricted to the variables of the innermost existential quantifier. More concretely, we need to store for each assignment to the innermost existential quantifier in a node T whether this assignment violates at least one constraint. Consequently, we require domain size to the power k many Boolean variables to store this information. This information, whether at least one constraint is unsatisfied, is guided along the tree decomposition. Notably, this allows us to get rid of the innermost quantifier block, and therefore this reduction R down provides kind of the reverse direction of R up. So this reduction basically trades an easier formalism for the cost of an exponential increased tree width. Let's briefly recall our running example and show basic ideas of this reduction R down. So the quantifier structure of R down is similar to the one of R up, where we invert quantifiers, but we do not need copy variables. So the former universally quantified w and x are now existentially quantified. The innermost existential quantifier block is not needed anymore, but we encode for each tree decomposition node all the assignments using variables of this innermost quantifier block. In node T1 we need to check constraints C2 and C3, and in node T2 we need to check constraint C1. That's why we only have these user variables for nodes T1 and T2. If y is set to 0, C3 is always satisfied, therefore only C2 can be unsatisfied, which is the case if w plus x is between 1 and 4. Similarly for setting y to 1 in node T1, if we set y to 2 or to 3 in node T1, actually both constraints can be dissatisfied. If we set y to 4, both constraints are satisfied. Similarly for node T2 and constraint 3. Then we need to propagate this unsatisfiability information from nodes T1 and T2 to node T3. For this we need auxiliary variables. These constraints basically express the following. If we have unsatisfiability for setting y to 0 in node T3, then we require unsatisfiability in at least one child node, so in node T1, or we have unsatisfiability for all the compatible assignments where we set y to 0 in node T2. Here we kind of simulate a universal quantifier. Last but not least, the reduction enforces unsatisfiability for all the assignments at the root node. With this reduction R down, we were able to show the QCSP lower bound. The underlying idea of the proof of this theorem is by reducing from Boolean QCSat L1 to QCSat L over some domain D, while our reduction R down. However, the reduction is slightly modified such that instead of Boolean variables for representing the unsatisfiability information, we use variables over domain D. This establishes the lower bound for domain sizes up to 2 to the k. However, the result can be easily generalized to arbitrary domain sizes by starting from Boolean QCSat L plus I.
This already brings me to the conclusion.
This work provides new insights on lower bounds for quantified constraint satisfaction problems for Treewidth.
Therefore, we established a Treewidth-Aware reduction that eliminates a quantifier at the cost of an exponential increase of Treewidth. We also provide the reverse direction for QCSP, namely a reduction that exponentially decreases Treewidth at the cost of an increase in the quantifier rank. We also show that our reductions are tight under reasonable assumptions in computational complexity, namely the exponential time hypothesis. For the future, it might be really interesting to see practical implementations, which might be particularly useful for solvers that actually use Treewidth. Finally, one might be curious about lower bounds for QCSP under stronger assumptions than the exponential time hypothesis, namely, for example, the strong exponential time hypothesis.